Ladies and gentlemen, boys and girls, lend me your ears. I want to show you this really neat vulnerability in U-boot that everyone's talking about. Not everyone, but I am. So if you run this script here, QEMU drive, QMU, bada bing, bada boom, you will see the magical values, the 41414141, the 41414141, and the 4242423E. What the hell is even going on? What are we talking about? Guys, we're talking about a vulnerability in U-boot, the bootloader that allows you to bypass signature verification by exploiting a vulnerability in the bootloader itself. Bugs like this are really, really neat because they actually invalidate an entire trust chain in the way that weird devices like this, like embedded ones and even ones that you're sit in your pocket, validate if they use U-boot. Obviously, this one does not, this one might. Anyway, I'm going to break down the bug, what went wrong, what you can do about it, and then also what the hell all this stuff means. The finding today was found by a company named Binarly. I've done videos on their stuff before. They do a really good job on finding vulnerabilities in like lower level. It's the name of the channel, by the way. Low level systems like bootloaders or BMC, board management controller, stuff like that. Again, not an ad for this company, just they do a lot of good work. So the vulnerability today is a stack buffer underflow, kind of hard to say, in U-boot during the FIT image signature verification, specifically in the FTT find regions functions. A lot of words said there. I'm going to go into what all that means here in a little bit. Okay, so enter U-boot, right? What is U-boot? Well, U-boot, kind of like the name of this folder that I had, I called it Das Boot. U-boot is a system that allows you to, in the embedded world, boot other OSs, right? So typically, the way these weird devices work is you have to bring them up. You got to get the board to BLI, you have to bring the CPU to live. And then the first thing that you run on a router like this is this thing called a bootloader. A bootloader is a piece of code that allows you to run other code. The idea being you don't have to make that piece of code know how to boot against every other CPU. You just bring the CPU up to the bootloader and the bootloader does the rest of the work, right? You can use that bootloader to run your OS like Linux or Windows or whatever. So if the job of the bootloader is to run code that we want it to run, why does RCE in a bootloader matter? Why does a vulnerability in U-boot matter to anybody? Great question. What actually is interesting about U-boot is its ability to facilitate this thing called verified boot, okay? There's this whole world of boot processes that the entire job is to make sure that code that is not meant to be ran does not run on the device. And we do this thing where we use a bunch of cryptographical algorithms using asymmetric encryption with like RSA keys and public keys and stuff to sign the software image before it tries to get loaded. And then using a public key on the device, we verify if that manufacturer signed image is actually what we want, right? Is it the proper thing that is allowed to run on this device, right? Because maybe we just don't want anyone to be able to run any software they want on random piece of Chinese router, right? Maybe that's a thing that they don't want. Okay. So the issue that happens here is when you go to boot with a U-boot image in this FIT format, this flattened image tree format, it is signed with a signature. It is basically taking a private key that the manufacturer owns. We use that to embed a signature cryptographically that says, yep, it was signed by this manufacturer. And then we use the public key on the device to verify the signature that it was manufactured, that is the proper image. But we can invalidate this entire signature verification process. We can upload and execute a piece of code that is not intended by the manufacturer if we can find and exploit a vulnerability inside of the bootloader. And this is exactly what Binarly did. And I'm sorry if you're with Binarly and I'm mispronouncing the company's name. I'm not very good at English. Okay, so stack buffer underflow in U-boot during the FIT image signature verification and FTT find regions. Basically, there's code in the bootloader that is finding different regions of the actual image itself. And the vulnerability is based on the same issue as one above, where we rely on the fact that FTT get name, which is a call that happens above, can fail. But this time we're interested in what it writes to the length argument upon failure, the error code. Very interesting. So there's this function called FTT get name that if for any reason in this searching of the image during this FTT get name process, where it's getting the name of a leaf of this image format, right? If for some reason it's searching and it finds that one of the leaves does not have a slash, right? So stir rchar is a thread safe version of strchar, which basically looks for a token in a string. If that fails, we set error equal to some value and we go to fail. And then in the fail label, we say if the length pointer exists, we are going to write out to that length pointer which should be the output of the actual length of the name. Instead, we're going to output an error value, and that error value is FTT error bad structure. And then notice that later on in the code, what we're gonna do is we're gonna say start copy onto end, the name that we found from that function, oh, and also end plus equals length. Well, the issue here is that length holds a negative value. It is a large negative error code. So instead of actually moving the end of that cursor of parsing forward, the pointer moves backwards. It'll go backwards by the size or the value of error bad structure, which is -11th, and then it will increment that and add a slash. As the amount of code generated by AI increases, one thing that scares me is the ability to maintain that volume of code. And that's why today's video is sponsored by CodeRabbit. CodeRabbit is an AI code review tool that helps engineers manage the world of AI-generated PRs. For one of my platforms, Low Level Labs, I added a feature to add bookmarks to the site, right? A fairly simple feature, but adding new API endpoints like anything does create potential new security vulnerabilities, and someone at the end of the day has to review this code. Now, CodeRabbit's new change stack feature makes this really, really easy. If you go to the PR overview page, you get a nice walkthrough of how the code changed, what the major changes are, and also it does some really nice things where it generates diagrams for you that you can easily put into your code's documentation. One of the hardest things about a growing code base is not only tech debt, but knowledge debt, right? Making sure there's documentation that explains exactly how the code works. Now, if you go inside the change stack, you actually see that there's layers here. What CodeRabbit is doing is breaking down the PR into the separate layers that it affects, right? We have the first layer, which is just the bookmark system, right? The single couple of Go files that maintain the bookmarks. But what's even more important is you get a very clean view here of, okay, now how does this system integrate to the overall backend API? This gives you your semantic diff of the code base, showing you what changes and how it changes as a function of the new feature. You know, and then we have the last layer here. We have the TypeScript interface that shows you how the new web page created for the bookmarks is integrated into the rest of the TypeScript system. Breaking down the PR like this, guys, gives you a much better idea of exactly what the PR does. You can go through and review the code, obviously, but knowing systematically how it affects the overall code base is a much cleaner path to a secure development lifecycle. And guys, CodeRabbit is used all over the world. You can actually try CodeRabbit for free at this URL below. Go try CodeRabbit out and see if your pull request needs some more work and if CodeRabbit can help you get there. Thank you for sponsoring the video, CodeRabbit. Let's get back to it. So the end result is like actually beautiful, right? So what you have here is a stack frame for the function in question, right? You have the stack frame for this function, and you have this end pointer, right? So it's end is this, and it's saying end plus equals length. So the pointer for end should go up and up and up. The stack grows more positively down. That is important for you to know. If you don't know that, you should know that watching this channel, damn it. But what's actually happening is we have another stack frame above us, and every time we exploit this vulnerability with these sections that have bad names that don't have a slash in them, we're actually subtracting the end pointer back and back and back 11 bytes at a time until eventually the end pointer points to the return address of the previous stack frame. And I know you're thinking, if you're like a binary exploiter person, you're like, wait, if this is its own stack frame here, isn't there nothing above it? Well, no, the contents of this buffer lives in another stack frame below it. So just trust me, this is how it works. So end goes up, 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 and then using a new malformed section name that does have a slash, we can write arbitrary data we want to the program counter and get it to return to whatever address we want. Again, if this is 32-bit like ARM, we're gonna have like AAAB, right? And if you're new to the world of exploitation, right, what's happening here by overwriting the program counter value, we now have the ability to arbitrarily run, or at least point the CPU to a place to run other code, right? Like we could have put code in like another part of the image, and we can like wrap around to like mprotect or whatever, or like set the page table entry to make it executable. We can do a bunch of evil stuff, right? The end goal here is that we're able to run code in the context of a bootloader that is doing signature verification without a valid signature, right? We are exploiting the code that is doing signature verification, and this could invalidate an entire secure boot-like process. I want to highlight that this in and of itself is not secure boot. This image would have to be signed by a secure boot key, like the manufacturer key that the actual motherboard has. But that being said, right, it's a really interesting primitive in the world of U-boot, of bootloader vulnerability. vulnerabilities. Not gonna dive super deep into a ton of these, but you have another bunch of vulnerabilities, like, you know, the same kind of bug, denial of service in U-boot using an FIT image signature because of an unchecked size value. There are other parts of the code that use a name pointer where that name pointer can be null pointer, and because of that, it's gonna do a bunch of other stuff. There's a whole bunch of interesting bugs on this write-up. I'll put it in the description below. But it's an interesting case study in the world of U-boot, of bootloader vulnerabilities. And the question for the class, the question that everyone probably wants to know the answer to, would Rust have fixed this? Sort of. So again, U-boot, the whole point of this is to, you know, have the CPU be brought up, the CPU runs a bootloader, the bootloader then enables the OS, right? We are at the super low level, name of the channel, by the way, in the boot process, okay? Now, doing this in Rust is actually like, there are these things called peripheral access crates, or these things called hardware abstraction layer crates that allow you to write code that is not unsafe for the board in question. That being said, doing things like raw MMIO that maybe there isn't a peripheral abstraction crate written for is very hard to do, and it always does depend on unsafe code. Even inside of the peripheral abstraction crates or access crates, there has to be, by the nature of how embedded software works, right? It's global mutability, which is what Rust is designed to get rid of. Inside of even this code, there has to be a piece of unsafe code, unfortunately. But that being said, it's possible, just not easy. And yes, Rust would have fixed bugs like this, right? You would, well, actually, now that I think about it, yeah, I don't think you're able to fix this bug because all you're doing here is writing out to a pointer and a value, right? And then from there, it's causing the underflow. So I'm not necessarily sure if that's the case. You can't do raw pointers in Rust, so there you go. That's the answer. Actually, yeah, no, the Rust error and not error, the OK and error type, the result type would fix this, because this is actually the classical issue in C where you're using the error code in the error state as the actual value slot, right? This is like the entire problem that the Rust T&E or Rust result type fixes. And before we leave, by the way, in the code here, what we're showing you, so what I did here is I wrote, I compiled U-boot, the vulnerable version, which there is no patch for, by the way, yet. I compiled U-boot to run in QEMU. QEMU is like a system emulator. It emulates an ARM chip. And then I ran U-boot and I tried to signature validate with the FIT image that has the vulnerable structures in it. And then by using this, I was able to take control of the registers that are put on the stack, right? So R10, the frame pointer, and then ultimately PC, where PC is the return address that we're going to execute next, right? And by doing that, this proves that I have at least the ability to point the CPU to other places in the code that I want to run my evil stuff, right? Now, obviously, the question of like NX and ASLR comes up, but that is a different question for a different video. Anyway, thank you for watching, guys. I appreciate it. If you like this stuff, check out my other stuff, and then give me a little kiss on the cheek. Okay, we'll see you later. Goodbye.